Hello, this is my English speaking practice, and I'm working on coding problems, and today's problem is range sum query, and solved, I've solved, and I've left this problem on the way. And yeah, this is what the AI generated. Yeah, so the core idea is like this. This is my idea, but I didn't implement this in time, so I asked AI to implement this idea, and I updated the range sum query mutable thrust to build a segment tree with RC left cell tree node and implemented new update and sum range. The tree stores start end ranges and subtree sums, so updates or queries are all over log n. Key changes: num-array now holds root and n. Tree node now stores start and in addition to bar. Added build tree, update tree, and query tree. If you want, I can add some tests to adjust index handling to match the exact tree code signature. Yeah. But I don't understand these types completely, so yeah, I wanted to learn this, and today I'm gonna learn these types, how it works, and so on. So before diving into let me submit this code like this. I'm not sure this works. Great. Okay, not bad. This solution is not fast. This beats 15%. So for example, this is one of the first test answer, and let me remember the problem is given an integer array and handle multiple queries of the following types. Update the value of an element and calculate the sum of the element of nums between indices left and right inclusive, where left is less than or equal to right, and implement the num array class. Initialize and update and sum ranges, and this function takes left and right, and we should return the sum of elements of the num between indices left and right inclusive. Okay. So this is one of the solution, and the structure num array stores n and v. What are they representing? N is the length of numbers that are given, and the v is it's hard to understand. I is shift to left means I don't know. This solution is hard to understand. So this is what I wanted. Maybe. So many solutions. Let me see this. n+1 and update. To use update function. Increment 1 since the tree big is 1 based. I cannot understand. Anyway, let me explain my solution. So since the query comes a lot, so the query should answer in constant, not constant, in a logarithm, in a logarithm time complexity. So I focus on I focus on the time complexity. So this function and this function should return logarithm algorithm, logarithmic O of log n. Yeah, I mean O of log n. And so it's basically like a tree, right? So let me explain about this. So for example, let's say the tree has 100 element. So yeah, we have 100 elements, and so the left index might be 0 and right index might be 100, right? And let's say the query is like this: left is 0 and the right is 60. So we have to return the sum value between this range, right? And return the answer in constant in logarithmic. Let me see the logarithmic. Right? Yeah, logarithmic time complexity, right? So this function is like split it into two function calls like this. Because this structure is like a binary tree, and it aggregates the sum of them between some range. So in this case, the tree have 100 elements, so the root of the tree have a total value of all of elements, right? So if if the query is 0 to 99, which is all of them, we can return in one step at the one calculation, because the root node should have the total value, right? Yeah, this is how it works. So but in this case, the query is from 0 to 60, and so this function cannot return immediately. We need to divide it, right, like this, and the left part would be 0 to 94 because there are 100 elements, so the half of them is like 0 to 49. So it means the left child node should have the total value between 0 to 49. So we can get this value at one step, one calculation, right? So the remaining part would be 50 to 60, right? But the 50 to 60, it's a little complicated for this tree structure, because the right child have a 50 to 99, right? So we don't use the value because it's not correct. So this function should also divide it, right? And how it is divided, concept is the same. So the right part would be divided into two parts as well. So 50 to 75 and 75 to 99. So so since we want to get 50 to 60, so we choose the 50 to 75. This is also overranged, so yeah, we do split it further, and it's like this. Left part would be 50 to 62. This is a little bit further overranged, right? And so we repeat this procedure, and we can get this left part 50 to 56, and the area, this area is included in this area, so we can use all of them. We can use this value, right? And this is not enough, and we need to get from 57 to 60. But the right part is like 57 to 62, so it's not matched, so we needed to divide it, and fortunately this the left part is from 57 to 60, so we can get the value at the very end of the 60, right? So we call this value and this value. We can get this value and this value. So finally we just add them, and we get the sum total value from 0 to 60. That's all. And in order to implement this logic, we needed to define the tree node, and tree node has a value, and also it has a range represented by start and end field, and also have left child and right child, right? And the num array has a root node and its size, right? So the new function, this is for constructing num array, so needed to construct root node, and it's so not easy to implement this. So so we can get nums, and we have n, its length, and if the n is not 0, we call the build tree function, and it takes nums and range, and let's see what it is. And this function returns RC left cell tree node. And this is like a container type. These are like a container type, but I don't understand them enough, so I want to learn right now through this tree. Okay, and build tree function. This have a recursive structure. So this function calls build tree function inside of it, right? And so the range might be the same, right? So if it's same, this function just return one node, right? RC new and left cell new and tree node new, and the value is the element itself. Yeah, value is the sum of the child element, but in this case there is no range. There is only one node, there is only one element, so start and end are the same, and the value is the element itself, right? Here is the base case, and otherwise so there is a range, some range, so we can get the middle index. So here is the procedure for division. So divide the range and call build tree recursively. And so this means like this means just literally building tree for this range, right? So this function returns the left child node, right? And the node might have the children. So because this is a recursive function, so we can assume the build tree returns left tree, and this build tree function returns right tree, right? So what we do here is calculate the total value, and so it means the left child's value and right child's value. We just add them, and yeah, the value is here, and we can create a new tree node and set the children, right? That's it. So this is not difficult, but yeah, it's so smart, right? We just care about index and the base case. That's all. Okay. So we can construct a tree. And in this program, we need to update and answer to the query, right? So update is like specify the index and value. Index and value, right? So how it works, let's see. If the root is none, if there is no root node, there's no child, there's no element, so we just return it. And the index is less than 0, this won't happen. Yeah, it's assured, right? Yeah, it's assured. Yeah, but the AI generated how to say, how do I say, because since the AI doesn't know the constraints, so it's, yeah, in general programming, yeah, this condition might be happen, but in this case we don't need it. And index, so this is also care about the abnormal case, but the index, the given index are assured in the range, yeah, in the range of the vector that is given initially, so we don't care about it. And also n is not 0, right? N is not 0, so we can simplify like this. So is none is not needed. So the root but the root is desirable to be option type, because maybe we can remove this and yeah, build tree and give it directory, right? Yeah. So let's see some range. It takes left and right. And so root is none, we don't care about it, and left is greater than right, we don't care about it, and left right, what is it? We don't care about it, we don't care about it. So change the type, and this is also not necessary. It's like a safeguard. It's like a safeguard. And the root is always exists, so this condition is not needed. Right. Oh yay. So we can left and right. What? Ah. Okay. So just call these functions. But yeah, this function is a little complicated. Update tree, let's see. Takes node. It'd be root node at first, and borrow it, and get the range, right? And if it's same, it means the node itself. So we just I see. So in this case, we want to update the element and the element and the node above it, because the if the value of the if the value of the child are changed, the parent would be affected, right? Because we can see this. So the value depends on the child's values, right? So in this function, aim to update the value of the element, and it causes to update the parent's nodes, right? So so this is for children. This is for most it's like a leaf node, right? In graph theory term, this is a leaf, and so we can update the leaf to value. It's like this. And otherwise we need to identify the range, which range would be updated, right? Because the index is just specify the one element, so so we can find out which range would be affected. So we can get a middle, and if the index is less than or equal to middle value, we have to go to left side, so we can get the left child and call update tree function recursively for left side, right? And otherwise, yeah, we just call for right side, right? Yeah, that's all. And this function is doesn't this function has effects and doesn't return anything, so it's like side effects. So at this point the update would be finished, and after that we are going to update the value itself, value of this node itself, and we do the same thing for left and right. I don't think this is we can make it more efficient, because at this point we can find out which side to be affected, to be updated, and the other side doesn't change. So maybe the value, yeah, node borrow left, borrow. Yeah, I see. Okay. But these calculations are not heavy. Yeah, so I think this is the best way. Yeah. So it's just access to the left child's values and right child's values and add them, right? Yeah. So theoretically, one side would be updated and the other side wouldn't be updated. But yeah, I think this way is the simple and best. Yeah. That's all. And let's see, query 3. So like this, and let's see query 3. Given the node and the range, so left and right, left and right. Okay. So if the given range are overlapped of the how do I say, if the given range are overlapped on if the given range overlaps with the range covered by the node, return the node value as is. If the given range fully covers the range of this node, return the node's value directly. Fully covers. If the given range fully covers the range of the node, return the node value directly. And yeah, so if the given range is not covered the node range at all, it's like this, we just return 0, right? And yeah, and otherwise, in this case, yeah, the given range partially covers the node range. So for example, partially covers, yeah. I see. Oh, this is so cool. So in my simulation, we had to check the middle index, and yeah, we checked how do we call the next function like this. Yeah, but as an implementation, it's like this. So fully covered or fully not covered, and partially covered. When partially covered, it means we don't know how to say, we don't know how to calculate it, right? But the query trees is a daily function for the situation, right? So given the ranges and this function returns the some value for this range. So when it's partially covered, we just call query tree like this, right? And for the right part, likewise, we the range are partially covered, right? So just call the query tree function. So the important thing is to define the base case like this. It's fully covers or fully not covers, right? So yeah. Because the node is updated, so this value would be changed. So it's like so it's like this and this, and this part is fully covered. So yeah, return the value. We can return the value, and this part it's not accurate. It's actually the node is like, the node has like this, and the range never changes. So in this case, fully covered, and in this case, partially covered. So just return the value of this node. In this case, not return this value, we call next, and the node is like this 50. Node is like this, and yeah, the range never changes, and we can see there is no overlapped area, so we just return 0 like this. So we can remove this. Yeah, so there are 3 patterns, and here is a base case, and yeah, for normal case we just call the query tree function recursively. It's so smart, and I like it. So let me submit this again. But the speed doesn't change. Okay. But what I wanted to learn today is these types. But I want to take a break for a minute. Take a break.